Symbolic execution was invented in the 1970s, but as I said before, it failed to take hold at that time as a commonly used tool, and this is because of limitations in both the algorithms and machine power available at that time. In the mid-2000s, two key systems triggered a revival of symbolic execution, and these systems were DART, developed by Godefroy and Sen and first published in 2005, and EXE by Kedar, Ganesh, Pavlovsky, Dill, and Engler, published in 2006. These systems demonstrated the promise of symbolic execution by showing it could find real bugs in interesting and complicated systems. And as such, it spurred interest in the topic, and many new systems have developed since. One important system that's made a big impact in practice is Sage. It is a concolic executor developed at Microsoft Research and grew out of Godefroy's work on Dart. It uses the technique of generational search that we talked about before. Sage primarily targets bugs in file parsers, for example, parsers of JPEG, Microsoft Word, Microsoft PowerPoint, and other documents. And it's a good fit for concolic execution because parsing files is likely to terminate, and it only needs to consider input-output behavior rather than complicated and interactive system calls. Sage has transitioned from research prototype to production tool. It's been used on production software at Microsoft since 2007. Between 2007 and 2013, Sage was used remarkably often at Microsoft. For example, it's been run for more than 500 machine years as part of the largest fuzzing lab in the world. It's generated 3.4 billion plus constraints, making it the largest SMT solver usage ever. It's been applied to hundreds of applications and found hundreds of bugs that were missed by other bug-finding techniques. For example, 1/3 of all Win7 WEX bugs were found by Sage. Bug fixes shipped quietly to 1 billion PCs around the world, saving millions of dollars both for Microsoft and the world. And Sage is now used daily in Windows, Office, and all of the big Microsoft products. CLI is another mature tool. In this case, it grew out of the work on EXE. It symbolically executes LLVM bitcode. LLVM is a compiler framework that's now in regular use at Apple. It compiles source language programs to an intermediate representation called LLVM bitcode, which is stored in a .bc file, and CLI will run on the BC file. It works in the style of the basic symbolic executor that we saw before, where it uses fork to manage multiple states. That is, rather than having an explicit work list, each time that it could go both directions on a branch, it actually forks another version of itself which proceeds along that branch, and a separate tool manages all of the distinct copies of CLI that are running at once. CLI employs a variety of search strategies, primarily random path and coverage guided, and it mocks up the environment to deal with system calls and file access and so on, and you can get it as part of the LLVM distribution. So looking at how CLI actually works, in the original CLI paper, published in 2008, they applied CLI to core utils, which is the suite of small programs that runs on Linux and Unix distributions. So these are programs like makedir and paste and sed and ls and things like that. What this graph is showing is the amount of coverage from CLI-generated tests compared to the manual test suite that comes with core utils. What this chart shows is that CLI is better at testing than the manual test suite. And we make that determination by looking at the lines of code covered by tests. In particular, the lines covered by CLI tests. From them, when we subtract the lines covered by manual tests, we see that for all but 9 programs, CLI covers more lines than the manual case. Here are a bunch of bugs that were found by CLI. These are the command lines that produce the bugs that cause these core utils programs to crash. Notably, the bugs involve very simple command lines and very simple input files, and yet they went undetected for quite a long time before CLI found them. So since these second-generation tools of CLI and Sage, there have been further developments. One of them is the Mayhem system developed at Carnegie Mellon by Dave Brumley and his collaborators, and it runs on actual executables, that is, binaries. Like CLI, it uses a breadth-first search style search, but it also uses native execution, combining the best of symbolic and concolic strategies. And as an interesting twist, it will automatically generate exploits when bugs are found, to shine a light on the fact that these bugs could, in fact, be security critical. In further developments from the Mayhem work, the same group produced MergePoint, which uses a technique called veritesting, and in this case it combines symbolic execution with static analysis. What it does is use static analysis for complete code blocks, so it will analyze a straight line piece of code, and in so doing, basically convert it into a formula that can be used by an SMT solver to ask a question about the program's execution. It will use symbolic execution for hard-to-analyze parts of the program, in particular loops, for which it may be hard to determine how many times it will run, as well as complex pointer arithmetic and system calls and so on. So this produces a better balance of time between the solver and the executor, resulting in better bug finding, that is, bugs are found faster, and more of the program is covered in the same period of time. Incredibly, MergePoint found more than 11,000 bugs in 4,300 distinct applications in a Linux distribution, including new bugs in highly tested code, like the core utils code from CLI. So there are many other symbolic executors. Cloud9 is basically a parallel CLI. JQt and Java Pathfinder are symbolic execution for Java. BitBlaze is a binary analysis framework, so like Mayhem, it works on binary executables. And Otter is a symbolic execution framework for C that is directed in that you can tell it which lines of the program you would like to execute, and it will try hard to get to those lines when performing its search. PEX is a symbolic executor for .NET programs. This unit has delved into the details of symbolic execution, a powerful technology that can be used to find security-critical bugs in real software. Symbolic execution can be viewed, on the one hand, as a generalization of testing. It uses static analysis to develop new tests that explore different program paths. We can also view it as a kind of static analysis, but one with very high precision and no guarantee of termination. And if it does terminate, its results are both sound and complete. Symbolic execution is used in practice today to find important bugs in production code. The Sage tool is used heavily at Microsoft, and the MergePoint tool regularly analyzes large Linux repositories. Symbolic execution tools of good quality are freely available, and we can expect that they, like static analysis tools, will penetrate more deeply into the mainstream in the near future.